Welcome back to Talk Tensors. Today, we're going to be taking a deep dive into a paper called CrystalGRW, Generative Modeling of Crystal Structures with Targeted Properties via Geodesic Random Walks.
Oh, yeah.
It's kind of a mouthful, but stick with us because this paper has some seriously cool ideas about how we might design the materials of the future using AI.
Yeah, you know what I think is really exciting about this paper is it's really focused on how we can use generative modeling to dream up new crystal structures.
Oh, wow.
And not just dream them up, but dream them up with specific properties.
Okay.
So you can almost think about it like an architect.
Yeah.
Who can design buildings and also tweak the building materials, like for strength or flexibility or even transparency.
So instead of kind of stumbling upon new materials by chance, we're talking about intentional design, almost like, playing SimCity, but at the molecular level.
Exactly. And this is huge because, traditional ways for discovering new materials is like trying to find a needle in a haystack.
Right.
It takes tons of trial and error, expensive simulations, years of research.
Oh, yeah.
And CrystalGRW is sort of offering like a shortcut,
right?
A way to generate plausible structures way faster, potentially saving scientists years of effort.
That's incredible.
Yeah.
Before we get too deep into how this model works, I think it might help to just kind of brush up on some crystal structure basics.
Totally.
I'll admit my knowledge of crystallography is a little bit rusty.
Of course. Well, let's think about a crystal as a 3D Lego structure with atoms as the building blocks.
Yeah.
And so the way that these atoms are arranged in a repeating pattern is called the crystal lattice.
Right.
Now, to describe this mathematically, we need a couple pieces of information.
Okay.
First, we need to know what type of atom each block is.
Right.
So is it carbon, oxygen, hydrogen,
So it's like having different colored Lego bricks for different elements.
Yeah, exactly. And then we need these things called fractional coordinates.
Okay.
Which tell us where each atom sits within this repeating grid. So think of it like coordinates, but scaled to the size of the repeating unit.
Oh, so kind of like a Lego instruction manual.
Yeah.
Telling you which brick to put where.
Precisely. And then finally, there's this thing called the lattice matrix.
Okay.
Which defines the shape and size of our Lego building block.
Okay.
So is it a square base or is it a rectangle base?
Gotcha.
So CrystalGRW is trying to generate all three of these things.
Okay.
Atomic types, fractional coordinates, and the lattice matrix.
Right.
To create new stable crystal structures.
Okay, I'm following so far.
Cool.
But the paper also mentions something called a diffusion-based generative model.
Right.
How does that fit into the picture?
Well, think about if you were to take a perfectly clear picture.
Okay.
And you were to just gradually add noise to it until it became like a jumbled mess.
Okay.
That's called the forward diffusion process.
Right.
A diffusion model learns to reverse that process.
Gotcha.
So it starts with that noisy image, and it slowly removes that noise to recreate the original image.
Oh, so it's like cleaning up static on a TV screen.
Yeah.
Until you can see the picture again.
That's a great analogy. And
right.
So CrystalGRW does something similar, but with crystal structures instead of images.
But crystal structures are 3D, and they exist in a space that kind of wraps around, right?
Yeah.
It's not like a flat image.
That's a really good point.
Yeah.
And that's where things get a little tricky.
Yeah.
Traditional diffusion models work in what's called Euclidean space.
Okay.
Which is like a flat grid.
Yeah.
But crystal structures exist in a non-Euclidean space.
Okay.
So a space that's curved and periodic.
Yeah.
It's almost like imagine trying to wrap a flat piece of paper around a sphere.
Yeah.
It wouldn't work that well.
Yeah, it'd get all crumpled and it wouldn't represent the sphere accurately.
Exactly.
So how do we work with these curved spaces then?
That is where this thing called Riemannian manifolds comes in.
Okay.
Which gives us the mathematical framework to represent and manipulate data in these non-Euclidean spaces. So it's almost like giving the model the correct tools to work with this curved paper.
Right.
So we can actually accurately represent this repeating nature of crystal structures.
Ah, I see. So CrystalGRW uses these Riemannian manifolds to handle the diffusion process in a way that respects the, unique properties of crystal structures.
Exactly. It's like giving our AI architect these special curved rulers and protractors to design in a world where things bend and loop back on themselves.
That's pretty mind-blowing. But to actually learn the intricate patterns and relationships within these structures, CrystalGRW uses something called EquiFormer V2. Right? Can you talk a little bit about that?
Yes. So EquiFormer V2 is a specific type of neural network.
Okay.
And it's been designed to be really good at understanding 3D geometric data, like our Lego crystal structures.
Yeah.
So it's almost like giving our AI architect this intuitive sense of how to connect those Lego bricks.
Right.
In a way that makes sense and is stable.
Okay, so we've got this diffusion process happening.
Yeah.
On these Riemannian manifolds.
Right.
And we've got this powerful neural network, EquiFormer V2, trying to make sense of it all.
Yeah.
But how does CrystalGRW actually ensure that the structures it generates are something that could actually exist in the real world?
Right.
Something that's stable.
That's where the concept of ground state structures comes in.
Okay.
And that's what we'll be talking about next.
Okay, ground state structures. That sounds important. What does that mean?
So the ground state of a material is its most stable configuration.
Okay.
It's the way that the atoms arrange themselves that uses the least amount of energy to like hold everything together.
Okay.
It's almost like finding that perfect balance for your Lego blocks so they won't topple over.
Right. So CrystalGRW isn't just generating any random arrangement of atoms.
Yeah.
It's aiming for structures that are likely to be stable and actually exist in reality.
Exactly. Now, traditionally, to figure out the ground state of a material, you have to use these really computationally expensive calculations.
Yep.
It's called density functional theory, or DFT for short.
Right.
It's like running a super detailed simulation to watch how all those atoms interact and find that like perfect arrangement.
I imagine that takes a lot of computing power and time.
It does. So to kind of like speed things up, CrystalGRW uses a little trick.
Okay.
It uses a machine learning force field called 7net
Okay.
to quickly estimate the forces acting on all the atoms within those generated structures.
Oh, that's smart. So it's like having a quick intuitive sense of how stable those Lego structures are.
Yeah.
Without having to actually build and test each one individually.
Exactly. And it turns out that this actually works pretty well.
Really?
The paper shows that a good chunk of the structures made by CrystalGRW had forces that were super close to the ground state structures.
Wow.
From like this standard materials database.
Okay.
So it seems like the model is definitely on the right track, making structures that are not just plausible, but likely to be stable in the real world.
That's really impressive.
Okay.
But let's go back to this idea of targeted property generation.
Okay.
The paper emphasizes that CrystalGRW goes beyond just making stable structures.
Yeah.
It aims to design for specific functionalities.
Right.
How does it do that?
Well, remember those like design constraints we talked about earlier? Wanting a building material that's both strong and lightweight and transparent?
Yeah.
CrystalGRW uses this technique called classifier-free guidance to nudge the model towards generating structures with those specific features.
So we're not just leaving it up to chance. We're giving the model some directions, some hints about what we're looking for.
Exactly. And the paper shows this using these things called crystallographic point groups, which describe different types of symmetries in crystal structures.
Oh.
So think about it like telling our AI architect, hey, we want a structure that has 6-fold rotational symmetry, just like a snowflake.
So with this guidance, CrystalGRW can create structures that not only look a certain way, but also behave in a certain way because of their symmetry.
Precisely.
Yeah.
And this is just like scratching the surface.
Right. In theory, this guidance could be applied to a whole bunch of other properties.
Okay.
Like conductivity, magnetism, even optical properties.
Oh, okay.
It opens up tons of possibilities for designing materials with specific functions.
Now, that's what I call really interesting. But before we get carried away with all the possibilities, I'd love to understand how CrystalGRW fits into the historical context of materials science.
Yeah.
This kind of research doesn't just appear out of nowhere.
You're absolutely right. CrystalGRW builds upon a long history of research in all sorts of fields.
Okay.
Computational materials, science, machine learning, theoretical physics.
Gotcha.
For centuries, discovering new materials was largely a process of trial and error.
Right.
Scientists would combine different elements, subject them to various conditions, and just see what happened.
Yeah.
It was a super slow process and often completely random discoveries.
Kind of like alchemists trying to turn lead into gold.
Kind of. But as we learned more about physics and chemistry, we developed better approaches.
A big breakthrough was the development of density functional theory, or DFT.
Right.
Which we talked about before.
Yeah.
DFT lets us calculate the electronic structure of materials and predict their properties from first principles.
Okay.
So we don't have to rely only on experiments.
So instead of just mixing things randomly, we could start making more educated guesses about what materials might be interesting.
Yeah. Exactly. But like we talked about before, those DFT calculations are really computationally intensive.
Right.
And that's where machine learning comes in.
Okay.
Machine learning offers a way to use the data we already have to make predictions and speed up those DFT calculations.
Okay.
So instead of running those long calculations for every single possible combination, we can train a machine learning model on a data set of existing calculations and then use that model to predict properties for new materials.
So it's like training a model to recognize patterns in those DFT results.
Yeah.
And then use that to kind of extrapolate to new unseen cases.
Exactly. And that's been a growing trend in materials science.
Okay.
We've seen lots of new machine learning techniques for predicting properties like stability, conductivity, even the crystal structure itself.
Right.
But CrystalGRW takes things a step further.
Okay.
It's not just predicting properties, it's actually generating brand new crystal structures that could actually exist.
That's a big difference. So CrystalGRW is built on this convergence of computational materials science.
Yeah.
Machine learning and generative modeling.
Exactly. It's a perfect example of how advances in one field can lead to breakthroughs in another.
Right.
And this convergence is only getting faster, leading to all sorts of new possibilities for materials discovery.
All right, so we've got the historical context.
Yeah.
Now let's get into like the nitty-gritty of how CrystalGRW actually generates those structures.
Okay.
The paper mentions something called geodesic random walks on Riemannian manifolds.
Right.
That sounds pretty intense. Can you break that down for us?
Yeah, it might sound complicated, but the idea is actually pretty simple.
Okay.
So remember those fractional coordinates, atomic types, and lattice parameters we talked about before?
Yeah, those are like our Lego pieces.
Exactly. Imagine they're just scattered randomly in a box.
Okay.
Now we need a way to arrange them into a stable structure.
Right, so we need some kind of like guide or set of rules to follow.
That's exactly what the geodesic random walks do.
Oh.
Think about a tiny ant walking on a curved surface like a sphere or a donut.
Yeah.
The shortest path for that ant to get from one point to another isn't a straight line anymore.
Right.
It's this curved path that follows the shape of the surface.
So I'm picturing that little ant carefully navigating that curved landscape.
Yeah.
So those curved paths, those are the geodesics.
Exactly. And those curved surfaces, they represent those Riemannian manifolds.
Right, the manifolds that provide the framework for understanding those non-Euclidean spaces.
Yeah.
Where surfaces bend and loop back on themselves.
Exactly. So CrystalGRW uses these geodesic random walks to kind of guide the arrangement of our Lego pieces.
Right.
Those fractional coordinates, atomic types, lattice parameters.
Yeah.
In a way that respects the unique properties of those non-Euclidean spaces.
So it's like our little ant is being guided by the shape of that surface, making sure it stays on track and doesn't fall off.
Exactly. And those random walks help nudge the arrangement of those Lego pieces towards something more stable and realistic.
Okay, I'm starting to grasp the genius behind this approach.
Ooh.
But the paper also mentions a score function.
Yeah.
What role does that play?
So the score function acts kind of like a compass for those random walks.
Okay.
It guides them towards areas that are more likely to be stable and realistic.
Also, it's like our ant has a map.
Yes.
That's telling it which way to go to find the most stable configuration.
Exactly. And the model learns that score function during training. It starts to recognize patterns in the data and figure out which arrangements of atoms are probably going to be close to that stable ground state.
So it's like our ant isn't just wandering around aimlessly.
Yeah.
It's learning the terrain.
Right.
Becoming more and more skilled at navigating that complex landscape of possible configuration.
Exactly. And that combination of those geodesic random walks, guided by that learned score function, is what allows CrystalGRW to generate all these really diverse and potentially stable crystal structures.
Okay, that's all fascinating. But what happens next?
Right.
How do we know if the model's actually found something new and useful?
Yeah.
And where does this novel notion section that you always talk about come in?
Yeah.
So we've got this model generating all these potential crystal structures. But how do we know if it's actually stumbled upon something truly novel? Something that hasn't been discovered before.
Yeah, that's a great question. It's not just about creating structures that look different. We have to compare them to databases of known structures to see if there's any overlap. The paper mentions comparing CrystalGRW's output to the MP20 dataset, which has like thousands of entries.
So it's like checking for plagiarism, but for crystal structures.
Exactly. And the paper highlights some really promising results. A good chunk of what CrystalGRW made was unique, meaning it was different from anything in the training data. It's like our AI architect is coming up with genuinely new designs, not just copying existing buildings.
That's impressive. But novelty isn't the only thing we're after, right? We also want those structures to be close to their ground state, that most stable configuration. How do we figure that out?
We touched on this before. DFT calculations are the gold standard, but they're super time-consuming. CrystalGRW uses that trick with the 7-net force field to get a quick estimate. And remember, the results showed that a lot of the generated structures had forces similar to known ground state structures. So it's a good sign that the model's on the right track, making structures that are not just new, but also potentially stable in the real world.
This is all incredibly exciting. But I'm curious, does CrystalGRW only work for simple crystal structures? Or can it handle more complex arrangements?
The paper actually goes into a really cool application predicting atomic types in perovskite structures.
Perovskites, I've heard that name before. Aren't those materials really promising for solar cells?
You got it. Perovskites have this specific structure, and they're known for being super versatile. They have a wide range of properties, so they're really sought after not just for solar cells, but LEDs, catalysts, even sensors.
So they're like the multi-tool of the materials world.
Yeah, that's a great way to put it. But they're also pretty complex, which makes them tricky to work with, especially when you're trying to predict which atoms will go in that perovskite structure.
That sounds like the perfect challenge for CrystalGRW. So
Yeah.
how does it approach this?
It uses this neat combo starting with diffusion on a simplex, which is a way to represent probabilities. Think of it like a multi-sided die, where each side is a different atom type. And the model's trying to figure out which side is most likely to come up for each spot in the crystal lattice.
So it's like rolling a die to figure out the atom type at each site, but it's not just a random roll, is it?
You're right. CrystalGRW uses that learn and score function we talked about to make sure the outcome is something that makes sense based on what it knows about perovskites.
So it's like a loaded die that's more likely to land on certain sides because the model understands how perovskites work.
Exactly. And the paper found that a specific setup using a softmax layer and something called the SO2 Atom module in EquiFormer V2 worked really well for predicting those atomic types in perovskites. It's like our AI architect found the perfect tools to build those structures with the right pieces in the right spots.
Now that's what I call a deep dive. I'm starting to feel like I could design my own perovskite solar cell.
Well, maybe not just yet, but you're definitely on the right track.
So we've covered a lot today. We talked about how CrystalGRW makes new and stable crystal structures, how it uses diffusion on those Riemannian manifolds, and even how it can predict atomic types in complex materials like perovskites. But before we wrap up, I'm eager to hear your novel notions for this episode. What kind of future research could come out of this work?
One really interesting direction would be to see if CrystalGRW could not only make the structure, but also predict its properties like conductivity or magnetism, even before we do any fancy simulations or experiments.
So like having a crystal ball that tells us how a material will behave before we even make it, that would be incredible.
It would be a game changer. Imagine being able to look at thousands of potential materials and know how they'll act without even going into the lab. It could really speed up finding new materials for all kinds of uses.
And how could we do that? What kind of research would we do?
I can start by training CrystalGRW on data that includes not just the structure, but also information about the material's properties. That way, the model could learn those connections and make better predictions.
That's fascinating. It's like teaching our AI architect to not only design buildings, but also to predict how they'll perform under different conditions.
Exactly. Who knows, maybe one day we'll be able to design materials with specific properties for whatever we need, all thanks to AI.
Okay, that's mind-blowing. We've explored the ins and outs of CrystalGRW, looked at what it can do, and even peeked into the future of materials science. I'm already wanting to read the whole paper and learn more. You can find a link to it in the show notes.
And remember, this is just the start. AI-driven material science is booming. Keep an eye out for more amazing research and exciting stuff in the years to come.
Until next time, keep exploring the world of machine learning and stay curious.